so stop making fun of Riley. Okay. Central limit theorem says alright, if a population is not normal, means it's not bell curved, but you take samples where the sample size is greater than or equal to 30, then the sampling distribution of the sample means is approximately normal. Also, if the population is just regular, normal, and you take samples of any size, then the distribution of the sampling means is also normal. Okay. So let's do an example down here. We're not going to do the formulas yet. Let's say that there are these numbers on a slip of paper and you put them in a box. The numbers 1, 3, 5, and 7. You randomly select 2 slips of paper. And there are, you can replace the piece of paper. Okay? So what's the possibility that you could get? You could get a 1 and then you could get a 1, right? What else could you get? A 1 and then a 3. You could get a 1 and then a 5. You could get a 1 and then a 7. And that's all the possibilities where you drew a 1 first. Alright, let's be systematic about it. You could also get a 3, 1, a 3, 3, a 3, 5, or a 3, 7. Are you guys following what I'm doing? What's next? 5, 1, 5, 3, 5, 5, 5, 7. Lincoln, what's next? 7, 1, 7, 3, 7, 5, 7, 7. Now, do you guys agree the probability of me getting each slip of paper is equal? Right, if I just without getting 2 things. If I just pull a piece of paper out, each one has a probability of 1/4. This is like the probability over here. It's a 1/4 chance. Sorry. Probability over here, let's say get a 1, get a 3, get a 5, get a 7. Here's 1/4 right here. They're all about equal. Do you remember what kind of distribution that's called? What shape that is when they're all equal? It starts with a U. Uniform. They're all the same. But if instead we start taking the averages, the means. So what's the average between 1 and 1? 1. The average is 1. What's the average between 1 and 3? 2. What's the average between 1 and 5? 3. What's the average between 1 and 7? If you can't think of the exact middle number, add them together, divide by 2. 4. Alright. Jocelyn, will you figure out all of the averages of all the 3s? Tristan, will you figure out all the averages of the 5s? And Lincoln, will you figure out all the averages of the 7s?
So add them together and what?
Divide by 2. Jocelyn, what'd you get?
2, 3, 4, 5.
Nice. Tristan?
4, 5, 6, 7.
Okay. Alright, so now let's do a probability distribution again. This time we're going to graph the means. Say it smells really bad?
Yeah.
Yeah, I know. Okay, so we've got 1s, 2s, 3s, 4s, 5s, 6s, and 7s. On the side, I'm going to count up frequencies, 1, 2, 3, 4. All right, how many 1s are there in our means? 1. How many 2s are there?
1.
There's more than 1, I think.
2.
2. How many 3s are there?
3.
1, 2, 3. How many 4s are there?
4.
1, 2, 3, 4. How many 5s are there?
3.
1, 2, 3. Tristan, Lincoln, you're letting Jocelyn do all the talking. Tristan, how many 6s are there? 2. Lincoln, how many 7s are there? 1.
Wait, what was that top thing called? You know, on the top?
Top thing?
The first one you know?
What do you mean the first one we drew? This?
Yeah.
This is just this is like the regular samples, so these are just the,
Well, like, what did you call it on the top?
oh, uniform. So this was uniform, they're all flat. Do you see how this one is starting to make a bell curve? So this is starting to approach normal. So once you start taking the means of a group, then anything will start to become normal. All right, the new formulas are, and this is complex to look at, but it is not that hard. This is a mu sub x bar equals mu. This is the mean of the means. The mean of the means is equal to the original mean. The standard deviation of the means, or the variance of the means, this is the variance of the means.
And what even is that?
That's a sigma squared with an x bar sub. So the variance of the means is equal to the old variance divided by n. And the standard deviation of the means is equal to the old standard deviation divided by the square root of n. So on average, here's what it looks like. let's say that this kind of bumpy distribution is what people are paying for their cell phone bills. It's not quite normal. It's a little bumpy, right? But then if I say, okay, now I'm going to pick 100 cell phone bills out of this pool, and I'm going to find the average of those, then if I graph the averages, it looks like this. Notice that it's tighter. And that makes sense because the chances that, look at the original. The original had not a lot of cell phone bills that were higher than 65 right here. Imagine it'd be really weird if you had 100 that were higher than 65 if you're taking out of this pool. So instead they kind of start to balance each other out. They tend towards the middle, and they become almost a perfect little bell curve when you take the means. That's the central limit theorem. Okay, so now let's use it. Second page. And when you get done with these notes, we can go to the library if you want. Anybody getting a headache? If you feel like you're going to, let me know. All right. Cell phone bills for residents of a city have a mean of $47 and a standard deviation of $9. So the old mean was 47. The old standard deviation is 9. And n, the sample size, is 100. Find the mean and the standard error of the mean of the sampling distribution. Go back to the front side. The standard deviation of the means is often called the standard error. All right, so the mean of the means is the same as the old means, so I'm going to write the mean of the means is equal to 47 still. And the standard deviation of the means, otherwise known as the standard error. To do that, I take the old standard deviation and I divide by the square root of n. So I'm going to take 9 divided by the square root of 100. You guys get 0.9? No? All right, go ahead and try example 3. You guys getting the same thing I am?
Mm-mm.
Did you take 18 divided by the square root of 4?
Yeah. I got 9. What? Oh, I thought it said 2 in my bed.
It did. I erased it.
That's 9.
Okay.
I got it right.
So the new z-score formula, instead of x minus mu over sigma, is x minus mu divided by sigma divided by the square root of n. So basically, this new formula for standard error is on the bottom now. All right, so what do you think the average amount of time a person 15 to 19 drives per day is?
An hour.
Nope. Less.
30 minutes.
25 minutes. Well, it's everybody 15 to 19. It's not just all drivers 15 to 19, right? You randomly select 50 drivers ages 15 to 19. What's the probability that the mean time that they spend driving each day is between 24.7 and 25.5 minutes? So notice this. See how now we're talking about, it's not what's the probability that that person spends this amount of time driving. It's what's the probability that 50 drivers, that the mean time. That's why it's the central limit theorem. It's the mean time. So we're going to do x minus mu over sigma divided by the square root of n. Thank you. So 24.7 minus the mean, which was 25, divided by sigma 1.5 divided by the square root of 50. When you put this in your calculator, you can do this all at once, but put parentheses around the top and the bottom. You guys get a z-score of negative 1.41. Okay, now you're going to do the exact same thing again, except for this time we're going to fill in 25.5. Do you guys know how to hit second enter and just replace stuff? It's a lot faster. So hit second enter on your calculator, and then scroll back and replace the 24.7 with 25.5. This time I got 2.36. Did you guys get the same thing? How do I find what the probability is between those two z-scores? You look up the numbers and do what with them? Subtract. All right, grab your z-score chart. right, we're going to do one more. What do you think the average room and board expense per year at a four-year college is? Room and board means food and housing.
A year, you said?
For a year. Four-year college. Well, they're supposed to be averaged out.
8,000.
A little higher. $9,126. Okay, so tell me how to do this one. We're talking about the mean room and board, so we're going to use the central limit theorem. Say it again. So it's the this part right here, 9,400 minus what? What's the mean?
4,700.
9126. This was the x. So this is the x minus mu over sigma divided by the square root of n. What goes on the bottom?
1,500 divided by the square root of 9.
Good. Okay, put that in your calculator. You guys get 0.55? Okay, now we need less than 0.555. So what do I do for that? Look it up on the chart. So you're looking at the z-score of 0.55. I got 0.7088. Now, is that the right answer, or do I need to subtract that from 1? That's the right answer, because it's a bell curve, and it always reads to the left. We're going to do example 6. We're going to wait for Riley tomorrow to do example 6. The example number 6 is just like showing you like a regular problem and then showing you a central limit theorem problem and the difference between the two and the wording. So you can actually do the whole homework assignment right now. This homework assignment is due on Thursday. So tomorrow we'll do example 6, and then we'll have time to work on the homework. Right now what we're going to do is go to the library so we can read.